Alright, so welcome everyone to this new stream of EagleFly, the experimental debugger. And as another stream, found impossible to continue streaming with the internet connection that I got. It's very poor, and I guess I would need to update and find another carrier or another service for my internet connection since we cannot stream this way. But things have to continue, and as always, I will upload all the videos onto YouTube once I finish. And I guess that's the way it goes. And and also, I mean, it has been so slow to upload videos here that I need some way of probably I need to change my internet connection service. But what can you do? Okay, for now, I guess I will start by saying that if you would like to post some questions on stream, on the Twitch chat, or on YouTube even, because we don't have Twitch right now, and I don't know when we're gonna get Twitch back. But if you want to post some questions, either way on YouTube, you can post them, and I will catch them after the end of the stream. And after the end of the stream, and whenever I saw them, I guess for now. But okay. So let's go back to where we were, and the last thing that we left off was that we solved this. Actually, I already have it here. Yeah, we were solving the Bezier curve equation for quadratics, which is this one. And as you can see, it's pretty. This is the Bezier curve for quadratic, and I mean, you can expand into basically this equation goes and goes, just goes and goes. Whenever you want a more complex Bezier curve, just add to the polynomial. You just add to the combinatorial thing. If it's either, this is for a 3-point step, it's a quadratic. For a 4-point step, it's a cubic, or anything, and that way goes on. And we found a cool information about Bezier curves here, so that we could solve for basically to really understand the real deep meaning about Bezier curves and how can we use them as a generic tool for our programs. In this case, for loading the TTFs that we want. That we want. Sorry, and so this is gonna be interesting since I think this is really cool how this Bezier curve is used into loading TTFs, and how the TTF is defined based on Bezier curves. That tells me that they are totally scalable since they are based on a function, and that function is based on parameters. Those parameters can be tweaked in a certain way, I guess. I'm not totally sure of this, just for the things that I've seen here. But once we get deeper into how Bezier curves are made, I guess we're gonna start implementing the Bezier curve itself and extracting the data out. We will be in a better position to extract the TTF and do something useful, I guess. That's the whole point of this for now. So let's continue on and see. So as you can see here, we have this Pascal triangle that basically is the combinatorial way. It tells you how combinatorics works, in the sense that, I mean, you can see here, for example, this place here. You see that combinatorics just tells you how many ways of, how many combinations, for lack of a better term, how many combinations you have from n number of elements whenever you whenever you uh, you have n number of elements and you want to mix just I elements. I don't remember, but I has to go from 0 to n. In this case, even though, let's go deeper into this. Forget about 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 all this. Oh man, I erased the one that was important. Forget about this. Forget about this. This now is good. Actually, I want to save this as yeah, this is the one. The combinatory of n r, which n is your number of elements from which you're going to combine, and r is the objects that you choose, or the objects that you're going to mix. N factorial r factorial minus n minus r factorial. Which is okay, so basically he has it here. So as for example, we can solve it. I go back here and try to solve it here. So we have, it's gonna be crazy now. let me do it a little bit different. Okay. We have n, yes, and k, which means n factorial, k factorial, and minus k factorial. And you know, if we expand, for example, the first term, if we say that n is equal to, in this case, 3, I'm sorry, 2 our maximum number, 2, I can go, yeah, I think this sucks. Oh, okay, so we have that, and we want to basically solve for 2, 0. So you have basically this, which is 0 factorial, it's 1, and 2 factorial is 2. So basically you have 1, and this should be the first element of our first coefficient. In this case should be oh man, I erased it, don't you? Well, it's this. Yeah, you have it here, you see? There's a 1 implicitly here, so we have that 1. Now the 1 minus t basically comes from the 1 minus t to the n minus k t to the k. In this case n is 2, k is 0, so this is 2, so it's 1 minus t squared plus t to 0, that's 1. And look, there you go, we don't have a t here, and that's all. hypercubic. So the bezier is a combinatorial of n elements in of I elements in n elements of I chosen elements into n test elements, I would say, of the polynomial that's 1 minus t to the n minus I and t to the I. So basically the binomial is the coefficient, and this is the 1 minus t n minus y ti. Okay, so he's just starting on using lookup tables instead of factorial, or using the factorial. most computer graphics purposes, we don't need arbitrary curves. We need quadratic and cubic curves. This primer actually does do arbitrary curves. So we can even try to, let me see. So we got that, how is it? It was 1 minus c square So if we want to define the cubic one, it would be 4 points and we will need to lerp this basically with another one that would be something like p1, p2, p3, and then I would do something basically the same, that is 1 minus t p I 3 of t equal 1 minus t times the first one, that's 1 minus t minus t square p0 plus 2t 1 minus t p1 plus t square p2 plus t of 1 minus t square p1 plus 2t 1 minus t p2 plus t square p3. And if we move this on, we get 1 minus t square cubic, sorry, p0 plus 2t 1 minus t square p1 plus 1 minus t square p2 plus 1 minus t plus t, well, yeah, t 1 minus t square p1 plus 2t square 1 minus t p2 plus t cubed p3, and that's the cubic, which if we simplify, we see that we have a cubic here, and we have a quadratic term here, which is 2t, and we have t 1 is t 2 square p1, so this will become 3t 1 minus t square p1 plus we cancel these terms. Can I? There you go. So now we have 1 minus t squared, so we have 3 also here, so it will be 3 3t squared 1 minus t 3t squared t squared 1 minus t p2, and then in the other parts we can say that we have t cubed p3 and 1 minus t cubed p0, and there you go. So as you can see, we have the same polynomial. Which now it's expanded to have the combinatorial so basically for any, I'm gonna say the bezier and k, I wanna oh Jesus, what happened? It seems to have a bug pain. Look at that. Look at that. Look at how, man, this sucks. I need to find a better drawing thing. But wait, for now I'm gonna zoom here. I wanna move into here. Well, whatever. So we have a bezier function. That's basically the summation of from I want to say from k equals 0 to n of the combinatorial of n and k times that's for the coefficients, and this is for the elements that we have inside y minus t. Okay, so now I see why it doesn't depend on p. That's why, because p stay constant across the function, we just put it inside. So we have 1 minus t to the n minus k and t to the k. for each one I can even put here times the point n, I guess, for it to, since it's a constant, this can be added or whatever. So I don't know why it's not, well, so this is a quadratic which just have three terms. The first term is a cubic, so it's a quadratic term, and it always, if we see back, it's 1 minus t squared. So 1 minus t squared S is the string. Okay, so he's mapping t for the function, and he's seeing the proportion, I guess. Okay, so the weight of the point to the total sum of the bezier function. So we have 1 point, and then we have another point. So you see here is like have P0, P1, P2, and P3. And here we have P0, P1, P2. So, interesting. So there's a relative importance of the weights, because the weights tells you where does that point will be. Since t just goes from 0 to 1, we can say that in the starting point, when t is 0, everything, the first term will have the maximum because it's 1 minus t, and the third term is going to be 0 because it's t, and the second term, that is 1 minus t times t, also is going to be 0 because it's multiplied by t, and it's 2 times that. Okay, that makes sense. And when t is 1, here it has the maximum strength for the third term and the minimum strength for the fourth term. But as you can see, the strength is not linear. the string has some kind of curve that moves around. That's really cool. And as for example, since it's a square, well, yeah, it has sense because it's square. And the second term is also nonlinear, and this is also nonlinear. Since it's nonlinear, all the points are nonlinear. That means that you will never find lines here. All are curves. So this is a quadratic. This is also quadratic, but in another form, and this is also quadratic. Cool. And for cubic, it's the same, but you add another one. Since now the terms are, the first is gonna be also, if you see, now it's not a quadratic, but it's a cubic. All of them are cubics. All of them define cubes, since they have like at least two curves or two kind of bounds inside them, you know, like holes. And for 15, you're gonna have 14 how do you say this, 14 concave spaces, I guess, concave curves, and which is the same. So as you can see, the first term and the second term will always have this kind of pattern where they like go in the opposite way, and the terms in the middle, they kind of make this crazy movement. That's really cool. Like they have like they're faced evenly. Okay, so for our bezier, we are the weights that we basically stated, and it's just a number that tells you how important that number is, how its strength it is. The weights are actually just the coordinate values we want our curve to have. Oh, interesting. So whenever we want to move those points, imagine we have the, without the weight, we have this structural form for a bezier curve. That bezier curve tells us all the relationships across the points and how those points will behave on depending on themselves. But when you are this extra one, what you're basically doing is a transformation of the points in space. So these are the terms of the polynomial, and these are the weights that we want. And we just say 120, 160, 35, 200, 220, 260, and 220, 40. And then we got this. rather than fixing the theorem and give you they fix the coordinates but gives you freedom over the interval. It's a spiral curve. These are the tangents. So there are a bunch of bezier curves here, you know. Every of these are bezier, and they join together. So why does, I mean, if we added a weight of 0, what will happen? If all the points would be in 0, 0, well, there will not be any bezier, isn't it? And that makes sense. And if we have a square where we have 1, 1, imagine that, for example, here we say that it's 120, 160 for the 4 points that define the curve, but we say instead for a quadratic that we have, I don't know, -1 0 and, well, something simpler. We have 1 0 0, 1 in 1 1 0, and the other in 1 1. So it would be it should be a bezier that connects all those 3 points. And if we say 1 1, yeah, basically it's a translation of it. Yeah, because if we add a whole term, imagine a vector. If we add a three-dimensional vector for a bezier, well, two-dimensional vector, we will translate the whole stack of points, which we don't want. We want to control each of the points wherever they are. So what that means is that it's some kind of a scaling. Since it's a scalar, each point, it scales the relationship between the points in a certain way. So it's more like a scaling. I guess so. So imagine that we have vectors in 2 dimensions. Imagine that we have a vector that tells me 120, 160, 35 to 100, to 20 to 60, and then there's a Hadamard that that multiplies each of the elements. In this case, is it would be the bezier itself as well, the same bezier in a vector, and yeah, it's a Hadamard. Or it can be even, well, it depends on how you see it. It can be the inner product of x times the each element of it, each element without the summation of the bezier. So we have the weights in x and the weights in y, and we have this inner product that adds them. Hold on a second. Okay, so we can try by doing some tests with this, so we can try to do some simple sampling of these beziers so we can see how they work, and with that we can do some crazy stuff, I guess. For example, here you go. Okay, so this is huge, man. This for doing crazy stuff. Getting 3D normals. Oh man, this guy gets really deep. Good. Newton Raphson. Yes. That's the bounding box, which probably also we want to look at the bounding boxes and stuff, because that's how we are going to draw the words itself. Type boxes. Okay, the minimum box possible. The curve inflections. Man, this goes really deep. The integral. Line intersections. Okay. There's curve intersection here. Okay, so let's try. was debug bitmap buffer. I know we should put it as a real 32. Okay, why not? Can't even assert. this is like for the pattern that we were trying to do, which we don't think we need it right now. this anymore. Boop, 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 boop. So here we grab the pixel and we say that the pixel is the buffer data and blah blah. We want to move the pixel every time, and also we want to say probably which scanline we're copying, so that we grab it. Yeah, okay. Probably want something like row, I guess. Equal to pixel and the row is going to be plus equal to the buffer width. This has to be the mean y times the mean x, and that will get us onto directly to the place we wanted. And also we want to move along. Also here we move a complete row down, and here we say that the pixel is equal to the row, and we also make the pixel to be moving all the time, and then we also, well, here's where we fill it, isn't it? And here we were doing some banana stuff here. We don't want to do that. We probably want to copy some other values, some we can pass here. We don't have it right now, but we have the buffer, but we can pass other buffer, you know, like I guess, which I mean, we don't have a bitmap right now. but we could try to, well, I'm gonna leave this for later, I guess. For now, I'm just gonna draw something relatively straightforward. Can make something like pixel. Have the pixel should be a U32 with the red or the blue shifted by 0, and the green shifted by and the red shifted by 1. So which in this, well, we don't care about the alpha right here, so and the red by 16 and this go like this I guess we could check if the value is negative here. I don't know, something like so. This is interesting since it's a top-down one with the height going down, and the buffer starts on the top-down uh, thing, but we're saying that the min x, so the min x should be also on the top left or in the bottom left. Mm, that's interesting. Since you're saying, okay, this is the min y, this is the top left, we will need first to move on until and then going upwards, which I don't think is the way we want. We probably want to respect that thing and just let it go, you know, like so that min x and min y, min x is correct, but the y is the one that I can see. Which of course I mean, just visually it's kind of weird, but um, the way we set the scan lines to be the buffer, that's the way it goes. I don't know if I have a, well, also we'll need to do the loader for the TrueType font, but I just want to do some kind of simple draw square thing that we can use for stutters. Okay, so this is gonna be well, well, the solver mapper, I mean, you want to draw something, like in the screen, like this is 0 0 or this is 0 0, which I don't know. I guess we're gonna start. Let's say for now, just, I mean, we're gonna test it, but let's say for now that we have a positive buffer so that we see things a little bit clearer. So instead of this, we have a positive buffer. Now min x and min y do the thing that we will expect it to do. This is busted, and now the min y will grab exactly what we want, and the min x will grab exactly what we want. So now we know that the max x minus x is always going to be which you think, I mean, if I am, well, probably this is 32 because 256 pixels will be the maximum wrapping. So and let's say that we want to for now well, I'm gonna say right here just for now. I don't know, some random stuff. or probably 256 to 256 uh 512 512 I guess. Oh yeah, they had to be reals. Are we running? We are not. Okay. So yeah, we just literally. Oh, just let me check something because if I say max x minus x, and that we grab it as a unit variable, we'll say something like whenever it's gonna be brighter on this part and dimmer when we reach max x, and the same for max y. It's gonna be brighter on the bottom and bigger and dimmer on the top on red, and in between is gonna mix it. That's the expectation. Okay, so if we go here and we're running, okay, so we don't have a red, we just have a blue, but we have this gradient stuff, which is, yeah, as we expected for the blue. And then why, well, you know, well, yeah, it's correct, 256 512. And what about the red? The red, the red, let me step onto it to see what did I do. Where is my, oh, this is, oh yeah, this is it. Okay, no, for example, look at this. I mean, well, I mean, that probably makes sense since we changed the version, but probably the debugger can search for the version and update the version that it gets. That's the whole point of that's the whole sense about letting the code, letting the debugger help you more on the task that you need. In this case, yeah, I know that I modify the project and we didn't compile it, of course. I guess if I set the project, well, yeah, because if I did have my project inside Visual Studio as our editor and we compile inside, I guess it does reload it, or probably it doesn't, and just which there's probably he doesn't do it, but I mean it's something that debugger should do to match and to load the code that you recompile whenever got it. I mean, it's a minimal thing, but I think it's kind of useful. So if I step onto there, okay, and I say 256, 256, 512, 512. And we have a buffer height. Oh, 540. Okay, it's almost on the top, just alright. So those are the masks. Blue, green, red. Right. We have a max. We don't get into them. We have pixel. We have min y 256, 960, min x. That's the pixel we're grabbing, which I think that's correct. And now we have a pixel. It's gonna be the row, and then we move the pixel every time, and we write it. Blue is max x minus x, which is 256. Well, that was crazy, but yeah, it didn't matter if it was bigger the range, because the mask will be will climb the value for the blue, and the red's max y. $256, so the red should be 256 also, and we shift it by the blue and the green and the red, and shift it out to 16. We got the pixel, so continue. So yeah, something's weird going on. What if I change it so it's the green and get it instead, you know? What, 1, 2, 3, 4, 5, 7, 8. There is no green also. So probably I have to clamp it. I am casting into U32. This shift is now U32. If I shift it by 0, it's a U32, and if I OR it with another U32 with another value, I don't know if I should do this, you know, and say that's a car. What about that? Does that work? Okay. Okay. This this is really cool. I want to do this by step so I can inspect it a little bit easier. So I want to be the color, and the color is going to be basically this, and then the color is going to be this. So what I want to see, it's I want to do this, oh my god, by steps, you know, and I want to say that oh my god, how many, there you go, we have colors there, but we now have this thing instead, and this thing instead. Okay, let's see what's going on. And even, I mean, I can even like break it a little bit down, but I think we can inspect it into the okay, in the inspector. So what I want to, but yeah, it should, I don't know, but let me see. We have the red, the green, the blue, and the blue mask. Oh, probably is because of the mask, I don't know. Yeah, blue and blue mask is 0. So the first bit's gonna be 0 because we happen to have a value that's 0. What is it? Yeah, because blue mask is 255 and the blue is this, so the first pixel is busted. Okay, and the red, oh well, the green, sorry, the green and the green mask, oh oh yeah, now I see the problem, because we need to shift first to then say that we have the correct yeah. Okay, I'm sorry for the thing that I did here. It was me being totally stupid. And yeah, what can you do? We don't need that, So now it's correct because now we shifted to the place where we have the mask, and then we like a shift. What I'm assuming is when you shift it, we have zeros on the other step, and we have, well, we don't care on the other because we will mask it. So I think this is correct. But yeah, before we were masking all the values because we we're not in the proper place. Okay, so if we go, we know that the green, well, now it's 0 because, hey, the color, it's 0 and then it's 0 and then it's 0. Next pixel, and then the color is 255, and the green, it's also 256, shipped by A, but the green mass is also P0. It doesn't change. Cool. So we have to go to the next Y. Let me go to the next Y. I run to the next one. I say the pixel is in the next row. Pixel is in the next row. I say, you know, I'm on Y, well, 257, and max Y 512. So the green value is 255, which is now something value. This is 0, and this is 255. Or 255 shipped by A. Well, I don't know what's the precedence in this. Okay. So why didn't it change it at all? Oh, another time, little bugs that happen. You know, little bugs. Okay, another time. So let's go to the next row because this one is going to be 0. The color blue is going to be 0, and then it should be, boom, we got it. Okay, there you go. So that was the thing that we were expecting here. Our beautiful rectangle. Which, you know, sometimes it goes crazy. And for now, I mean, this is cool because now we have the bounds to draw. In this case, it can be text or anything that we want to. This is a really basic one. We have some input there. So yeah, I think we're setting things really good. And we can continue. This tomorrow. Also, let me see. Well, yeah, this is, yeah, it's a how can I say, in X, all times in X you have a line here that's black and a line here that's black, and the red is brighter here and the black is, oh yeah, so this is the cyan and this is the green. the cyan and the green, the cyan and the green, and this is the greener and this is the bluer. Okay, yeah, that's correct. We can change the color. Of course, there you go. And as you can see, yeah, this is busted. Just because of the way that we did it. We should, well, not just for now. We'll have the lower one, but seems to, am I looking it correct? I think it's correct. I think it's correct. But that was just because of the higher pixel and what we were doing with the pixel. But that would, I mean, we don't care too much about that because, I mean, that's why not, this is not what we're gonna do for the others, where this is just a test. But yeah, I guess this is good. We're gonna stop here and we will continue for the next stream, which is nice. I guess we are getting somewhere. We probably want to test the bezier so we can see how it works. I mean, it's just a simple test, not a crazy one. Just for seeing on or to if we did it, if we practice on the bezier, we can do, I think, better to extract and understand the data inside the TTF. That's our main goal, to parse the TTF and to draw a letter into our little rectangle that we set up today. Alright, so that would be all. Please, if you have any questions, we'll have a stream right now, but you want to post them on YouTube or on Twitch or whatever you want. Well, just YouTube and Twitch for now. I'll be happy to answer them. And yeah, for now, I will pause. I will pause and upload the videos on YouTube. And yeah, I think that's all. Okay, so I will see you the next time. Bye bye.